this next talk, I'm particularly excited about, especially with all that's going on in the water industry. It's always good to hear more from the engineering side of the house. And hear more from the water industry, but with everything going on, I think it's just really critical. And so we have two folks that'll be joining us for this talk. Gentlemen, you can go ahead and turn on your cameras and get into position as you'd like. We've got Andrew and Gus. And Andrew, besides being like 30+ year engineer and working in the water industry, and I believe you and Gus worked at the same utility, which Gus reminds me was the cleanest, best water in the United States or world, I think is probably his reaction. But you also have a special connection to SANS, where you were on the first organizing committee for the first SANS SCADA summit. And so, I'm also interested in your perspective as you kick off, kind of what you think, 16, 17 years later, as you're seeing all these talks and the things that you're doing. But your experience as an engineer who early on was advocating cybersecurity in this space. It's just extraordinarily relevant and amazing to hear. And then Gus, of course, someone I get to work closely with. Gus is a professional engineer as well, who worked at the water utility, who was a SCADA manager, who early on was advocating for cybersecurity discussions as well, and what it can mean to process safety and security and really reliability. And so without trying to take any more of your time, I'll just say, for the rest of the audience, listen up, like two true engineer experts understanding this problem early on to really talk about the cyber physical safety discussion. We are just extraordinarily lucky to have you both. So thank you.
Thank you, Rob. It's really great to be here. Yesterday, you and Tim were wondering out loud when the first SANS ICS summit happened. And I can act as a SANS historian in this case and say that the first public one anyhow was in 2006. And this is the actual conference brochure.
That is
And it's
awesome.
kind of fun because it was called the Process Control and SCADA Security Summit, but the words process control are like itty bitty print because like who knows what process control is, so we'll call it the SCADA Security Summit. So like Rob said, I was on the organizing committee along with a lot of awesome folks, and that included Eric Byers, who, by the way, was already on his entrepreneurial path the year before the summit. While he was teaching at the British Columbia Institute of Technology, he was busy selling DVDs on hacking PLCs, and we bought one, and I appreciated it at the time because it was a great eye-opener for our SCADA group. So my name's Andrew Hildick-Smith. I have a background in civil engineering, and for the past 30 years, I worked at a large water utility. And for 17 of those years, I was responsible for the SCADA system, its maintenance, operation, and security. In 2001, I began worrying about the cybersecurity of our system when a visiting team from Sandia National Lab pointed out that the dual home server that we had separating our OT system from our IT system really wasn't great security. So we put in a firewall, and other changes followed. And then we got a little more security motivation when one of our managers gave an interview that was published, essentially saying that it was impossible for anybody to break into our SCADA system. I'm like, oh no. I'm thinking all eyes are on us. And then in 2010, my security worries grew with the disclosure of Stuxnet, and we realized, we could only make it difficult, but we couldn't stop a determined adversary. Some new changes followed, and some of which are the essence of this talk.
Hi, everybody. I'm Gus Serino. Thanks for tuning in today. Andrew and I are both, as Rob mentioned, pretty passionate about the subject, and so I really appreciate the opportunity to talk. So I'm a control systems engineer. I have about 20 years experience with design, testing, programming, troubleshooting, and securing ICS systems. For the last 2 years, I've been on the professional services team with Dragos, working with lots of organizations, trying to help them better defend their control systems. But for about 15 years of my career, as Rob mentioned and Andrew mentioned, I was part of the SCADA team for a large water utility. And so most of my experience is from the asset owner perspective, trying to implement security of our ICS system while supporting production operations as well. I'll kick it back to you, Andrew, to take it through the first part.
Gus and I are going to cover the following topics. What are the standard water system goals, threats and risks, protective approaches? We'll explain cyber-physical safety systems, identify other important breach preparation steps, describe how to establish cyber-physical safety systems at your utility, and then wrap it up. All of this is specific to water utilities, but many of the process resilient steps can be applied to other critical infrastructure sectors. There's some slides included in this talk that have vendor equipment images, and I just want to point out they're there as convenient examples, not endorsements. Next slide, please.
Yeah, sorry, something happened here. What the heck? There we go. Sorry, Andrew.
Okay, so during this slide, I want you to partially ignore me and watch what our resident artist, Ashton Rodenheiser's up to. And not to put too much pressure on her, and I think she's amazing. I don't know how she does what she does, but I'm totally curious to see how she draws this part of the talk, since she's the one that illustrated this slide. I'm thinking maybe it'll be like a Norman Rockwell painting of himself, or E.C. Escher drawing of his hand, or maybe she'll just take a much needed break. But so every water utility is expected and required to provide safe drinking water at appropriate pressure. They all have the same basic infrastructure elements. There's one or more water sources, a transmission main, onto a treatment plant, a pump station that pushes it up to elevated storage, and then it flows by gravity to the consumers. And while our talk is focused on the drinking water side, a wastewater system is practically a mirror image, facing the same operational challenges, threats and risks, and opportunities for resilience. Of course, the potential consequences of a breach there are much different. Next slide, please.
I've lost the ability. Okay, there we go.
Ah, good. In conflict with the water service goal is the risk that no matter how good your cyber defenses are, a skilled adversary can breach them and possibly cause intentional or accidental physical infrastructure damage or hazardous water quality conditions. What is the significant for all of us is that with every year, there's a growing level of sophistication and an increasing pool of adversaries with the skills to execute serious targeted attacks. It no longer takes a state actor. A couple of years ago, I asked an ICS security instructor whether his class of college students had the skills to pull off a sophisticated control system attack. His answer was yes. Next slide, please. Recognizing that a disruptive control system breach is possible, water utilities need a fallback cyber breach goal, and that is to maintain a reasonable level of water service and to restore full service as quickly as possible. We can do that if we can prevent physical damage to the system, if we're prepared to operate manually, and we can securely restore the control system. Next slide, please. So what are the parts of a water system that are vulnerable to disruptive or destructive cyber attacks? They're some of the same things that normally fail during water system emergencies. Fortunately, that means utilities have experience with responding to these problems and may already have redundant components or backup plans in place. The three broad categories are pipe breaks, water quality issues, and equipment failures. An example of what can happen in a normal emergency can happen in cyberspace is the case of extreme overdosing of sodium hydroxide into the Spencer, Massachusetts water system in 2007. Nearly 100 people went to the hospital with rashes or burns. It was caused by a human error compounded by an alarm problem, but it's very similar to what the intruder tried to do at the Oldmar, Florida water system last month. Next slide, please. In this talk, we'll focus on high pressure events and the risks of breaking pipes. And an important reminder is that every water system is different. They share similar features and equipment, but the individual risks are unique. Some systems may face a risk of water hammer, which is a high pressure spike caused by a rapidly closing valve. Utilities can assess whether they might have that kind of risk with a surge analysis. Another possible overpressurization risk is having too many pumps come on at once. This could damage weaker pipes. Utilities can assess the existence of that risk with system hydraulic modeling. Now Gus will talk about protective approaches.
Thanks, Andrew. So number one up here represents all the things we need to do as defenders to secure our control systems from a technology point of view. Things like patching and network segmentation and firewalls and VPNs and hardening and all that stuff. And if we need to do them, they're really important, of course, but these defensive strategies are applied to the technology side of the control system and to ultimately to secure the process from the technology side of the ICS system. Many of us in engineering, we emphasize the importance of securing the control system from the physical side as well in a parallel effort. When I say the physical side, I'm talking about the control system interface to the process, the pumps, the motors, the valves, the instruments, not the network side. Of course, these strategies only need to be applied when it makes sense and when the risks posed are outside what's tolerable for the organization. So traditionally, process control included systems that would automatically regulate the process to be within normal operating pressures. And so Andrew said in water systems, that's maintaining pressure or keeping the treatment process stable. The idea is as the process changes, the control system compensates to maintain stability and normal operation. If the process conditions are not kept within those bounds, the system generates an alarm that prompts an operator to take corrective action. If the process continues to deviate, then automatic shutdowns and protective functions engage, but those protective functions are usually within the primary digital control system. In some cases, with particularly high hazards, safety instrumented systems or SISs are designed into the process, but they're typically not deployed in drinking water systems. The idea of an SIS is usually it's a digitally based control system distinct from the primary control system. It has independent monitoring and shutdown capability to safely stop a process before harm is done to people or personnel. And then as a last line of protection, mechanical things like pressure relief valves, rupture discs, overflow channels, and things like that are there to prevent catastrophic damages. These layers of protection and process control engineering haven't traditionally accounted for ICS-focused cyber-induced hazards. We've seen enough cases where the attacker bypasses digital protections, gains access to the control system, and abuses the automation to disrupt the process. And so even if there's a protective function programmed into the control system, when the attacker has access to manipulate it, those things can be defeated. So organizations can apply cyber-physical safety systems to address this, but there's a need to understand basically three things to get started. What are the acceptable bounds for normal process operation? How is the control system built to support that? And what's possible through cyber means to disrupt it? In the cases where an operator, if they were alerted in enough time to an abnormal operating condition, then they can intervene and prevent unacceptable consequences. In those cases, an independent alarm system outside the mechanism of the primary control system can provide that function. In other cases, operator intervention may be too late or not enough, and so a cyber-physical safety system is required. Those mechanisms outside the primary digital control system function either actively or passively to prevent those high consequence impacts. In either case, we need to understand and pre-plan our response actions when any of these events occur. So as I mentioned, in some cases, it can be enough or preferred to simply back up the situational awareness of the operator with an independent alarming system. It may be obvious, but worth pointing out that the approach here, it can provide valid process data to the control system, to the control center, even when an attacker is masking their actions by manipulating the information on the HMI. So how does independent alarming work? We need to get an indication of an abnormal process condition into the control room independent of the primary control system. There are many variations to do this, but here's an approach as an example. So we take a direct hardwired signal from the instrument itself. Could be through tying into the 4 to 20 milliamp loop or an alarm contact off the instrument or transmitter. It's some way to get that data as close to the process instrumentation as possible. Shouldn't come from the primary control system or over the network. Next, we take that signal and we tie it into an independent telemetry system, like a data logger shown in the picture up here. We can transmit that information back to a server, and we recommend the servers not on the same network segment as the control system, could be on the corporate network, could be on some other segment. However, the alarming capability does need to make it into the control room. And a side benefit of this approach is that this data can be used in cases where the primary digital control system is down or communication is down. So the operators have access to the most critical parameters of the process. So they can continue to monitor those parameters while recovery and repair efforts are happening. And then if the architecture supports it, you can take it one step further. If you can feed those common signals from both the primary control system and the independent alarming system into the historian, for instance, now you have two copies of the data from two distinct sources, and you can compare them and create a discrepancy alarm that gives an indication of something going wrong in the process. So, as I mentioned, in cases where operator intervention may be too late or not enough, then applying a cyber-physical safety system might be the right approach. The kinds of systems we're referring to today don't require cybersecurity expertise. In a lot of cases, they can be identified, designed, and implemented by utility personnel, and they can be included in designs for new systems or retrofitted to existing systems. It doesn't just prevent cyber-based consequences, which we all agree can be low-frequency, high-consequence events, but they can prevent problems from normal malfunctions and human errors as well. And one really important thing to note is that these systems, they need to be carefully designed and implemented so they don't introduce a new source of risk or process disruption. They should take action outside the limits of normal operation, and we need to consider any potential effects on the process when they fail. So I'd like to present an example of a cyber-physical safety system that was implemented because of concern in one area of the water distribution system where there was a potentially vulnerable pipe. We looked at it and asked, is this a place where there's a risk of mission impacting damage? So we did some analysis, including hydraulic modeling, and determined that this was a place we needed some protection. We could envision a scenario where someone with bad intention and access to the control system could do something simple to cause a break. To mitigate the possibility, it was suggested that the pump station that fed into that distribution area, we retrofit pressure switches downstream of each pump that would cause a trip when high pressure was detected. It's not a normal cybersecurity protection, but it would certainly prevent damage to a weak area of the system when a malicious cyber event or even an accidental malfunction occurred. And so, like any good asset owner, we transferred that risk of our good idea onto someone else. And so in around 2014, we added the high pressure shutdown into a construction contract for a new pump station that was coming online that was also going to feed into that distribution area. And like I described, the contractor implemented a pressure switch downstream of the pump. When the high pressure was detected, it would shut down the pump. It would also send a signal to the PLC for an alarm in the control center, and then latch the pump off at a relay panel that needed to be reset locally by the operator. So in this example, we knew the system, we understood the areas of concern with it, and we came up with a mitigation strategy that would prevent damage that would affect our fundamental mission. We didn't need to consider attack paths, 0 days, remote access, anything like that. We just had to apply the right engineering to prevent a really bad day. So after that new pump station came online and the high pressure shutdown was tested and validated, our in-house staff then refined the design a little bit more and then installed it at the sister pump station where the problem was initially observed and the solution was designed. So from the perspective of not introducing additional risk into the normal distribution system operations, we set the trip setting on the pressure switch just higher than the normal startup pressure of the pump would be enough to add the protection but not impact the normal operation of the facility. So this picture shows the inside of the pressure switch and illustrates how a simple electromechanical system in the right place can prevent significant damage. One important point to make about these systems, again, is that organizations need to incorporate them into normal maintenance cycles, calibrate them, test them periodically, include them in operator training so they're understood and they're remembered and they work when they're called to engage. And so beyond that example, a couple other examples of mitigation within water systems to prevent equipment under control from causing damage, actuators. So these are the machines that move valves. They have gearing and other components that control the rate of travel for the valves. And so as Andrew mentioned, water hammer is one concern in water systems. If you've ever had a chance to observe an operator changing valves in the system, they do it very slowly. One of the main reasons for that is to prevent water hammer. And so we tune the automatic control of those valves to also operate slowly for the same reason. However, if the gearing of the actuator is such that it's capable of traveling fast, there's a setup there for water hammer. And so our recommendation is that organizations go back and verify that the gearing of their actuator is configured properly to limit the rate of travel to only what's needed for normal and emergency operations and not faster. From a cyber physical perspective, if an adversary can manipulate that valve to move fast enough, there's potential to do damage. And then another example is it's often a bad assumption to assume that industrial equipment is sized perfectly. It's also not a good idea to assume that maintenance activities will go according to plan, as we know, right? So sometimes those circumstances come together to help us identify when there's a need for a cyber physical safety system. We know of one situation where a problem occurred with an hydroelectric turbine, where there was a calibration going on for the instrument that controlled the flow into the turbine. What happened was the automation called for more flow into the controls. The automation called for more flow, and the control system opened the wicket gate beyond what's normal. If you're not familiar with a hydroelectric turbine, a wicket gate is a series of adjustable vanes that allow flow into it. In this case, when it opened too far, the turbine went into overspeed, high vibration alarms happened. It was okay, but a bad situation. And after the incident investigation occurred, the end result is the mechanics ended up welding a piston that moved the wicket gates, so that regardless of what the control system called for, the turbine was physically limited in how much water it would permit to enter the unit. So, like, we know that these are not new concepts, they're not rocket science, but they can be really effective in limiting some of the worst case scenarios that come from accidents or malicious cyber activity. And so this one last example, I wanted to talk about the recent Oldmar incident. And so first I want to say that Oldmar was not unique in having insecure remote access to the control system. We find this more often than we like, honestly. But the operator was on the ball in this case, noticed the incident in real time. The city's officials then shared the information publicly. And so as a community, we're really fortunate to have this near miss as a learning opportunity. We can use it to highlight the need for discussions around secure remote access to control systems, and that in many cases, we need to have cyber physical protections. Said it several times, in situations where there's a possibility to harm people by manipulation of the control system through cyber means, we need to consider a prevention on the physical side of the attack vector. So in this example, on the lower right-hand side, you see the pH analyzer. As I described, similar to the independent alarming section, taking a hardwired contact from the high output on the transmitter can be wired into a relay panel that it simultaneously halts the sodium hydroxide pump and sends in parallel alarms to the PLC for the primary digital control system, as well as an independent alarm to the control system. So this example covers both independent alarming as well as a cyber physical safety shutdown. This would have prevented an even more complex attack than what occurred at Oldmar from harming a consumer. So Andrew and I, and a lot of other engineers that we've collaborated with over the years, support the idea that physical protective systems are something that should be more commonly considered in control systems for water and other industries. And I'll pass it back to you, Andrew, to talk about some other resilience mechanisms in response.
Okay, thanks, Gus. Gus has just described how cyber physical safety systems can help prevent physical damage or hazardous water quality conditions. In order to fully achieve our breach goal of providing a reasonable level of water service and restoring full service as quickly as possible, we need to do a few more things. They include identifying and isolating core processes and control elements in order to protect their process functions, establishing a plan for manual control in order to maintain water service, and being prepared with the cyber incident response plan so we can securely restore the control system to full operation. Next slide, please. There are certain processes and equipment within a water system that are essential for basic service. They need to be identified and protected from the rest of the OT network, which we assume will be breached. A good approach is to connect the essential processes to the rest of the water control system with direct I/O. So hardwire using 4 to 20 milliamp signals without a network connection. The same approach should be taken with essential control elements such as critical pumps and valves. This may take away certain maintenance and monitoring capabilities, but it preserves the device for manual control if the IP network is compromised. Keep in mind that integrated Bluetooth and Zigbee communications built into a lot of this equipment may create a vulnerable bridge to equipment that you've already isolated in other ways. Also, HART protocol and other non-IP smart protocols may introduce unintended access. Next slide, please. The second breach preparation step is being ready to manually control the water system. Under a breach scenario, when the full control system cannot be trusted and has been intentionally shut down by the utility, manual operation of the water system is required to maintain at least basic service. That service might be at a reduced pressure or quality, but at a bare minimum, it needs to provide firefighting capability. In a simple scenario, you can have one operator at a pump station manually turning on and off a pump while another operator is at the water tank calling in updates on the water level by converting values from an analog pressure gauge. Water treatment is more complicated. Ideally, components of the water system can run in a local auto mode that retains some of the automated features and puts less staffing pressure on the utility. This could be established through a single loop controller or other system automation that is independent of the full SCADA system. And it's super important to practice manual operation and to do this in incremental steps and under calm conditions. Next slide, please. A third important breach preparation is cyber incident response. It's required if you want to restore full automation and get back to full service as quickly as possible. It provides an essential path for understanding the extent of a compromise, how it occurred, and preventing its return once the system is restored. I won't go into details of this slide, but I do want to repeat an important point that Ron Brash made yesterday. Keep spare devices on hand, as you never know when you might get bricked. Now we'll switch gears and cover how to go about implementing cyber-physical safety systems at your utility. Next slide, please. We think there are 4 important steps to establishing cyber-physical safety systems: getting together the right people, setting the stage with the right mindset, identifying the critical systems and vulnerabilities in your utility, and creating and vetting cyber-physical safety systems that match your need. Next slide. Gathering the right people. This is the most important part of the process. And that means getting together the people who understand the water system in different ways, including operators, engineers, managers, maintenance staff, process control staff, and someone with a hacker mindset. The great thing is that everyone in that group has a different perspective on the water system's operations and vulnerabilities. They have their own responsibilities and concerns. If just Gus or I attempted to do this on our own, it would not be a success. You need the insights that come from diversity. Next slide. Everybody in the group has to adopt the mindset that an adversary can do anything they want to do. It actually takes effort to get that point across. Nothing is off limits unless physics prevents it. It's as if you have welcomed the adversary into your utility, given them a complete insider's tour, pointing out system vulnerabilities along the way, and then said, have at it. Next slide. The group needs a moderator to help keep them on track and focus while they mentally work their way through the complete water system, identifying critical components and unacceptable consequences as they go. Next slide. Once any serious adverse events are identified, you have a group of experts at hand that can work through possible solutions. Ideas need to be critically examined to make sure they are simple, and as Gus said, that they do not introduce new vulnerabilities of their own. Next slide, please. Okay, we're coming down the home stretch. What Gus and I have talked about are measures to take to protect the water treatment and delivery process. There are other related approaches that you can look into. One is CCE, which is promoted by Idaho National Lab and was presented by Andy Bachman in a 2018 paper and at this summit. Other methods include cyber process hazards analysis and crown jewel analysis. And by the way, I heard a rumor that if you tweet Andy Bachman with a message that says CCE rules, he'll send you a free copy of his new book. So he's going to have to confirm that though. Next slide. We all recognize that a determined adversary can achieve many goals. We highlighted approaches that a water utility or other critical infrastructure organization can take to maintain a reasonable level of service and return to full service as quickly as possible after a serious control system breach. We recommend establishing simple, independent cyber-physical safety systems that can prevent damage to critical water infrastructure and hazardous changes to water quality. Fortunately, these safety systems can be designed, installed, and maintained by in-house staff without advanced cybersecurity skills. They can be both inexpensive and successfully retrofitted into existing systems. A valuable complement to cyber-physical safety systems is independent monitoring and alarming. This can protect against process masking by an adversary, possible damage from slow consequence process changes, and identify dangerous water quality changes. After a serious process control breach, an adequate level of water service can be maintained and full service can be restored if we can protect equipment and infrastructure from damage with cyber-physical safety systems, keep core processes and elements available for use by sufficiently isolating them from network hazards, keep water flowing by establishing and practicing manual and local auto operations, and finally getting back to full service securely by establishing and practicing cyber incident response. This is a lot to do, but the great thing is that it's doable. It takes advantage of a broad mix of staff and their skills and helps keep your process resilient in a world with cyber threats. Okay, next we have some references and an opportunity for questions.
All right. Thank you so much. That was fantastic. And your Slack, it's just lit up with lots of love. And hey, can I get you to present this to my engineers? And all sorts of fun comments. So thank you for going through that. I thought that was fantastic. I'll go ahead and start hitting you with a couple questions. The first one is really looking at kind of those independent kind of safety systems you were talking about putting in place, the protection systems. The questions, kind of the intent of the question is, it can be really hard to create the events that would test those without damaging the system or just like getting into an operational environment where you're allowed to. So how do you think through testing them or feeling very confident in what they're providing?
That is a tricky question. You're absolutely right. Especially retrofitting to existing systems. When you're incorporating them into designs of new systems, it's certainly a lot simpler during the commissioning process. But in retrofitting, especially where you have potential causes of breaks, so it's really about bench testing instruments if you need to, understanding, measuring what the real process parameters are when you're starting up, for that pressure switch example, for instance, starting up the pump and understanding what that pressure profile is through startup and through normal operation, and then bench calibrating those instruments so that they activate when you need them. You obviously can't test the real thing. It's a little bit of faith there. You're absolutely right on that. So
it's good faith though.
Science.
Sorry, go ahead.
I was thinking maybe another example of if you look at the Oldmar case, and you might, Gus had given examples of like monitoring, independent monitoring and interlock, but you could also say you could design the pump size, right? So you might have the wrong pump size now, but you go back and look at what you really need. And for sort of that size town, you might be pushing about 25 gallons of sodium hydroxide a day. And so you can size your peristaltic pump to match that, with a little bit of buffer. And when you figured out the real details, and it's more complicated than that, but then you'll typically have N+1. You'll have like an extra pump, and you can practice using that extra pump with just running water through it. And so there are ways to do things on live systems. In at least water utilities often have an extra device, that +1 device.
No, perfect. And that makes sense. And the next question actually goes right back to Oldmar, which I think you were already getting to. I think there was a lot of discussion of, well, we're just lucky the operator saw it, but that's not exactly true. I mean, there's a lot of protection built into the system anyways, and then manual testing and all sorts of wonderful things. But on the other side of the spectrum, there's plenty of you can't do it because there's so much. And it's like, well, we have accidents anyways, and there's this balance. But regardless of what happens, as it gets to the individual, the question is more probably a chemistry question more than anything. But at what level in parts per million, or just kind of abstract it out if you can, would sodium hydroxide become obvious to the average person of like, don't drink that, it smells or tastes horrible in this case instead of smells? And at what, or is it just a point at when it's bad enough, you're already experiencing burns or similar?
Yeah, I don't think either of us know the real answer to that, but we can sort of extrapolate that instance at Spencer, Mass. It's a pretty similar sized town to Oldmar, and their normal dosing over the course of the day was 25 to 30 gallons a day. And in their case, they had a very concentrated slug that went in over the course of the night before the regular water pumps kicked on and pushed it. So all this can sort of visualize small numbers of gallons, and if the you're in the 30s gallons over the course of a day, but you put it on all at once. That was the amount that people got physical skin burns and rashes. And so I don't know what parts per million or parts, what percentage that is, but that can help you kind of imagine.
Yeah, absolutely. No, that's fantastic. Gus, anything before we end out?
No, I mean, none of this stuff is not easy, but organizations are the best suited to be able to do this because they understand where the weak spots are. They understand, the operators know what they're concerned about doing. And so that information is really relevant to the people who are working on the control system and understand where these things may lie. And so just have an open mind. There's ways to do it on the physical side too. I mean, it's not going to solve everything, but the big ones you might be able to hit. So.
No, fantastic. And I love that as well, because it's always interesting when somebody looks at something for the first time, you're like, oh, this really complex problem that everyone's working on. There's actually this one easy solution. It's like, okay, sit down. So as you noted, it's not easy. That's a great way to end it out. So anyways, fantastically well done. Thank you both for presenting.